Welcome to our comprehensive deep dive into LeetCode problem number 733, Flood Fill. In this video, we will thoroughly explore the problem statement, analyze sample inputs and outputs, discuss multiple approaches including both depth-first search and breadth-first search, and explain their trade-offs. We'll provide step-by-step explanations, walk through both Python and Java implementations line by line, and break down the complexity analysis. By the end, you'll master how to solve flood fill efficiently in interviews and real-world coding, equipped with practical tips and advanced insights. Let's begin. Let's break down the problem statement for LeetCode problem number 733, Flood Fill. You are given a two-dimensional grid called image, with each cell representing a colored pixel as an integer. Three more integers, SR, SC, and new color are provided. The task is to start at the pixel located at row SR and column SC, and change its color, and all four directionally connected pixels of the same original color to new color. The fill should proceed only in the up, down, left, and right directions, and not diagonally. The transformation applies recursively. If a neighboring cell matches the original pixel's color, it too is recolored. In example 1, the starting pixel at 1, 1 has value 1, and all surrounding pixels of value 1 that are connected are updated to 2, while other pixels remain unchanged. Continuing with example 2 for LeetCode problem number 733, we see that the starting pixel at position 0, 0 has value 0, and we are asked to recolor it to 0. Since the starting pixel already matches the new color, there is nothing to change, the image remains the same. Now, let's examine the constraints. The image can be up to 50 by 50 in size. Each pixel value and new color can range from 0 to 65535. The starting row and column are always valid indices. Key edge cases include starting pixels that already have the new color, large contiguous regions of the same color, and making sure we do not go out of bounds during recursion or iteration. Understanding these details helps us prepare a robust solution. When analyzing LeetCode problem number 733, Flood Fill, two main strategies emerge: depth-first search and breadth-first search. Depth-first search is straightforward and intuitive for grid traversal. It uses recursion and easily touches every needed pixel, but can hit recursion limits in some languages if the filled region is very large. Breadth-first search, on the other hand, avoids stack overflows and handles larger regions safely by using a queue. Both approaches have similar time and space complexities when implemented thoughtfully. For this problem, DFS is usually preferred for its concise code, but BFS is the safer choice in environments where stack depth is a concern. Now, let's go through the step-by-step algorithm for LeetCode problem number 733, Flood Fill. Begin by checking if the starting pixel already has the new color. If so, we return the image unchanged to avoid unnecessary work. Next, we store the original color at the starting position so we know exactly which pixels to change. We then traverse the grid using either depth-first search or breadth-first search, sticking strictly to four directional moves. For each pixel, we check boundaries and see if the pixel matches the original color before coloring it and visiting its neighbors. We stop upon reaching pixels that either lie out of bounds or have a different color. This approach prevents infinite loops and ensures only the correct region is filled. For implementation, recursion is handy in DFS because filling and visiting can happen in the same function. In BFS, you might use a queue to keep track of the pixels that need to be filled, adding neighbors as you color each one. There is no need for a visited set, as you color each pixel precisely once, marking it as visited. Always remember to return the entire updated image after processing. Also, note that diagonal connections do not count, only direct neighbors are valid for filling, as specified by LeetCode problem number 733. Here is the Python implementation for LeetCode problem number 733 using depth-first search. We define a solution class with a floodfill method. First, we get the original color at the starting pixel and check if new color is the same to avoid redundant work. We then set up a helper DFS function for recursion. This helper checks boundaries and color matches and recurses into each direction up, down, left, and right. The image is updated in place and returned at the end. This DFS ensures all valid pixels are colored efficiently. Here is the Java implementation of LeetCode problem number 733 using recursion for depth-first search. This code uses explicit method arguments with Java static typing and encapsulates DFS in a private method. Logic for boundary checking and coloring matches our Python approach. Both implementations update the image in place and return the result. Pay attention to class structure, method signatures, and the use of argument types in Java compared to Python. Let's walk through example 1 for LeetCode problem number 733, flood fill. We start with the initial image and set the pixel at position 1, 1 to our new color, 2. From there, we check the 4 direct neighbors. Each neighboring pixel with value 1 is colored to 2. We continue recursively, processing each new colored pixel's neighbors. When we reach pixels that are not 1 or move outside the grid, we stop. Through this process, all ones connected 4 directionally to our start are colored to 2, resulting in the final image. For example 2, when the starting pixel already matches the new color, our algorithm checks for this immediately and returns the original image unchanged. This early exit avoids unnecessary processing and prevents infinite recursion. Similarly, whenever we encounter this situation in large areas or different starting positions, the logic ensures no surplus work is done and the function operates efficiently. Let's discuss the complexity for LeetCode problem number 733. In terms of time, each pixel is checked at most once, resulting in a worst case of O(m*n) operations for an m by n image. Space-wise, DFS uses recursion, so its stack may grow to O(m*n) for a uniform grid. BFS likewise could use a queue of similar size for the same. Both approaches meet the problem's constraints and handle max sizes comfortably. Between DFS and BFS, the main trade-off is risk of stack overflows with extreme DFS recursion, but for images up to 50 by 50 as specified, recursion in Python and Java will suffice. Flood fill is a classic grid traversal technique, appearing in many related LeetCode problems like number of islands and rotting oranges. In interviews, it's common to be tested on edge cases. Ensure your code checks for immediate returns when the new color matches, and always use only 4 directions as specified. Correct boundary checking prevents data corruption and out-of-bounds exceptions. Marking pixels as visited through coloring is efficient. Prefer BFS over DFS when stack depth may be a limitation. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!